We're going to keep in with the water theme here. This is going to be a little bit more of a start to finish on water resource management associated with shale energy development. So we're going to look at where the water is being sourced from, how it's being transported, how it's being stored, how it's being utilized, and how the wastewater or the produced fluids are being managed. So sort of a to Z on water resources management here. So as I'm sure you probably heard yesterday, shale gas or shale energy development can be a rather water-intensive endeavor. Without water or some other fracturing fluid, these shale reservoirs really just don't allow gas to readily flow. So these reservoirs need to be fractured to increase the permeability of the shale and therefore produce the oil or gas or natural gas liquids from these formations. So this shows a fracturing site up in northern Pennsylvania. You can see the wells here. It's a relatively busy area. The well pad itself might be on the order of about 5 acres or 2 hectares roughly, and you've got a series of water storage tanks, pump trucks, sand vessels, all blending this together. Very importantly, of a control van where they're monitoring the fluid injection rates and the pressures to make sure everything's going according to plan. And so that's really a critical part of this, because if something were to deviate, say the pressure were to drop suddenly, the engineers on site would want to make sure that they understand what's going on in case they need to shut down the operation for some unforeseen reason. So this is just a close-up of the wellheads with all the lines feeding in to the wells where the actual fluids are being injected from the surface down into the reservoir. Again, it's pretty amazing how this is all orchestrated. The average well, to drill it, to fracture it, to produce it, based on the numbers some of our folks have come up with, you need over 400 people to make all this happen. And it encompasses about 150 different types of jobs. So it definitely creates jobs to make all of this happen. The drilling process itself might use between, say, 300,000 to 400,000 liters of water, and that would be the water used for the drilling muds and the cements to make sure that the wells are properly sealed. But it's the actual fracturing process that uses the majority of the water, so you're looking at maybe somewhere between 12 to 20 million liters of water to actually fracture the shale. And then, depending on which particular shale reservoir you're working in, you're going to get a return. A certain percentage of the fluids that you've injected down into the shale are going to come back up. And as I'd mentioned during the last talk, before the well's actually producing gas, you get an initial slug of water, commonly called flowback water. And then once the well's actually producing gas, you get the produced fluids. They're really sort of this, coming from the same place, but again, the produced fluids tend to have higher concentrations of total dissolved solids and some of the other contaminants. What goes into the mix? We showed you some sort of long tables in the last presentation, but in general, you just have a few classes of additives. Again, the majority of it is going to be water. It's going to be on the order of 90 to 95% water. The reason I like this particular chart is because it shows that they're using recycled water, and this is from Chesapeake Energy, one of the second largest natural gas producer in the United States. And again, that's that water that they're recycling for hydraulic fracturing operations that is this flow back and produced water that's coming out of these wells. And so what that's doing is offsetting some of the use of fresher sources of water and also minimizing the disposal of that water, say, through deep well disposal. About between maybe 5 to 10% of the mixture is going to be a sand or other proppant to hold open these fractures. If you were to pressurize the shale and then relieve the pressure, the shale more or less is going to close back up on itself. I mean, it might stay open somewhat, but it's going to pretty much close back up. And so what the proppant does is it keeps those fractures open. So if you can get a couple grains of sand in between those fracture faces, that's just enough of a width of an opening to allow the gas to flow out of the shale formation. And then it's the other, in many cases, less than 1%, or in many cases we're seeing less than 1/10% of the mixture is the chemicals that more or less optimize the process. And in general, you get 3 to 4 different kinds of families of chemicals added. You'll get again the friction reducer, which in essence makes the water more slippery. So as you're pushing it down the basically 5-inch pipe, or roughly 12 centimeter, 13 centimeter pipe, you're going to have a lot of frictional losses if you're trying to push on the order of perhaps 12,000 liters per minute down that pipe. You would lose a lot of your pressure. So what the friction reducers do is minimize those pressure losses. You're typically looking at light petroleum distillate or polyacrylamide are commonly used to achieve that purpose. What that ultimately translates into is you need less pumping trucks at the surface, less horsepower, therefore less diesel or other fuels are being burned on site to generate the pressure to push the fluids down there because you're reducing that frictional loss. You get antibacterial agents are added in to more or less make sure the water is sufficiently sterile so you don't have bacterial growth down in the well that could have some undesirable impacts on the well's production or potentially produce hydrogen sulfide, which is poisonous and would also require treatment of the natural gas. And then, again, a scale inhibitor is used to minimize any downhole chemical precipitation, which could plug up those fractures. In some cases, companies will use basically what they call an acid package, which is primarily hydrochloric acid. The primary purpose of that is to clean out the horizontal section or the open section of the wellbore. Because when they drill a well, they're going to have perforations that are the size of a dime, and they need to clean out those perforations and make sure there's no residual cements or rock debris in there. And so that hydrochloric acid helps break that down. So again, just to kind of reiterate, that the additives here in a little more simpler terms than some of those longer tables we showed in the last presentation. This is a nice graph from the EPA's hydraulic fracturing study work plan. It just kind of shows the overall water management on a site. So you're bringing water in, whether you're trucking it in or whether you're piping it in, and that source of water could be from a stream or a river. It could be water that comes out of a groundwater well. It could be water that is wastewater from a municipality's treatment plant, or perhaps even an industrial wastewater, or perhaps a water from a quarry or a mine that's sitting there. So we're seeing some innovations in looking at the use of alternative water supplies, waters that may have already been degraded on some level because of it's been used in an industrial process, for instance. But wherever the water is coming from, it needs to be blended with the chemicals that we just covered, injected down into shale, open up the fractures, allow the hydrocarbons to be liberated and flow into the wellbore, and then again you get some return of fluids back. Depends on which formation you're in. In the Marcellus, you tend to get about 10% of a return of those fluids. In some of the other formations, you might get 50% or more of a return of the fluids that were injected down in there. So these fluids, again, need to be stored in some environmentally sound way so that there is no potential for any sort of environmental or water quality impact. Again, we're seeing more and more of the water being stored in tanks on site, minimizing the potential for spills. And then ultimately, that water is either going to be recycled on site or taken to a treatment plant for either recycling purposes or disposal purposes. And we'll get into more depth on that. So some of the considerations for where the water is going to be sourced from would be just how close is the potential water supply to the drilling area, and whether there's actual access to that water. The regulations vary across the United States. In the eastern half, basically the philosophy is there's enough water for everybody. In the western half of the state, it's pretty much first come, first serve. So depending on what your water rights laws are here in Columbia, you would have to figure out how shale energy development might fit into your existing regulations, or perhaps how they might need to be modified accordingly. Depending on, again, what the climate is where you're doing the development, would also hinge on just how available water is on a seasonal basis. In Pennsylvania and much of the Appalachian Basin in northeastern U.S., we have a lot of rainfall. So in general, water is not in shortage, except during the summer months, it tends to get drier. And we do see that some of the operators are not allowed to use the water from their stream or river withdrawal point because the flow is dropped down. And so that brings up another critical consideration, is just how available is water going to be on a seasonal basis, and how do you monitor what is an appropriate amount of water to withdraw. So what we do in Pennsylvania is look at the pass-by flow. How much water do you need to pass by your withdrawal point to make sure that the aquatic health of the stream or river is protected, and to make sure there's enough water for other downstream users, whether it's a town or other industries that rely on that water. The quality of the water needs to be considered. Oftentimes a stream or a river of average water quality is going to be sufficient for the use of hydraulic fracturing, but in many parts of the U.S. where we've had historic mining practices, especially coal mining, the water in the stream or river might have elevated levels of metals like iron or aluminum. It could have elevated levels of sulfates, and it could have low pH in the range of maybe 3 or 4 pH units. And so that water quality might not quite be compatible with hydraulic fracturing, and so it might require some treatment to condition the water for that purpose. The schedule needs to be considered here. There's a fairly rigorous regulatory permitting process to get access to water that's going to take, it's going to be measured in months or maybe even a year or more. Many times the companies are under pressure to do their drilling to meet certain contractual obligations, and the timing of the drilling might not match up with the timing of access to water. And so that needs to be proactively planned out to make sure that the permits are in place to legally withdraw the water, so when the company needs it, it's available to them. And again, that then ties in with the permitting complexity. If a company's trying to get water from a pristine stream that lots of people use for recreational purposes and fishing and things like that, they're going to face much more scrutiny from the regulators than if they're trying to pull water from a stream that's been degraded, say, due to historic coal mining practices. And actually, this photo here is a stream that's been degraded. You can see that orangish color to the water there. That's as a result of abandoned coal mine drainage. And so this stream actually can't support aquatic life. There's no fish in this stream. And then at the end of the day, of course, the budget needs to be considered in all of this. Moving water from point A to point B can be a rather expensive endeavor. I've seen estimates that the water management costs to do one well might be somewhere between 5 to maybe upwards of 20% of the cost of a well. So if you're looking at maybe $5 or $6 million to drill and fracture and develop one well, those costs might be in the order of maybe $250,000, or it might be upwards of $1 million. Just depends on how far the water needs to be transported and how efficient a particular operator might be. We touched on the pass-by flows and the need to make sure that there's sufficient downstream flow. This is a limit that's going to be set by the regulatory agency. So you'll need to demonstrate, well, there's this much flow in that stream on an annual basis, and therefore if we withdraw this volume of water, we're going to leave this much water in the stream. But stream flows vary. And so we're actually now seeing some of our river basin commissions look at regulating the withdrawal volumes based on seasonal flows to make sure that not too much water is removed from the hydrologic system during any given season. This just shows a sort of a unique gauge where it actually sends a signal down, bounces back up, and will tell automatically what the stream level is and therefore what the flow of that level is. And then that feeds into this particular operator's withdrawal system. And if the stream level drops below that critical threshold point, it shuts down the system so they can't withdraw water once the stream flow drops too low. So that's actually kind of an innovative automatic technology that's being put out there into action. Again, moving the water from point A to point B is probably one of the most intense activities with the whole process. It tends to be one of the more visible activities. You're seeing water trucks move water, but we're starting to see companies put pipelines in place that's taking the trucks off of the roads. An average well, if you're going to use, say, 5 million gallons of water, might take 1,000 tanker trucks to get that water to that site. So that's 2,000 trips because the trucks are going up and they're coming back. And in many cases, the roads were never designed to handle that kind of activity. The roads begin to crumble. Just as an example, the energy industry in Pennsylvania expended about $500 million in road repairs over the course of just a couple of years, the last couple of years, to repair the roads that were never designed to handle the level of traffic. So there's a sort of a hidden cost in there. Not to mention it's very expensive to truck this water. So that's why, again, if you're trucking the water management costs are going to be much higher as opposed to piping the water. So again, if I had to put a number on it, I would say about 75% of the water in the Marcellus is being trucked currently, and about 25% of that water is now being piped, with more and more piping occurring, which tend to be about 50% of the costs of trucking. So it's very cost effective for the companies. Not only that, but it also makes more sense. It takes the trucks off the road and the potential hazards associated with that. So again, this just shows one of the pipes being put in. Oftentimes when the gas lines are being put in, as denoted by these yellow posts, they're putting a water line in while they have the trench open, because the cost of pipeline isn't the pipe itself so much as it is the trench and the excavation work. But again, there's still a lot of trucks on the roads out there. This is a sort of an innovative project where a company put in roughly a 15-kilometer pipeline from the source and ran it up rather severe topography. down a valley and out to one of its most remote well pads. And so just when I looked out my hotel room this morning and saw the big mountain out here, I said, well, yeah, I can see where there could be some topographic challenges here in Colombia. And we faced many of these in Pennsylvania and other states around the U.S. where it's just not perfectly flat. But the technology out there, does make it such that you can pipe water fairly significant distances under severe topographic conditions. And this particular operator estimated by being able to pipe that water ultimately to all of their well drilling pads, they're going to take 70,000 trucks off the roads during the build out of this site, and probably save on the order of $10 million in trucking costs along the way. So it's sort of a win-win scenario. And then there's also going to be sharing agreements with operators who have other nearby leaseholds, so that each company just doesn't put in their own water infrastructure, that they share the infrastructure. It divides the costs up, and it just makes good sense. It lessens the surface impacts and land disturbance. And this is actually the pumping intake for that piping system I just showed here. So they have the pump. They run it through some filters just to get out the suspended sediments, and then run it up through the pipelines to deliver it to the well fields. This is actually one of the more unique intake structures. So sometimes you'll just have basically a pump in the creek, or you might actually build the intake so it forms the part of the creek stream bed bottom, so it's less obstructive. So there's less of a hazard associated with it. So you can kind of see there's a grate in here built into the stream, and the water actually flows down through that. And it actually also somewhat helps maintain the water quality. You don't get as much suspended solids. The water won't be as cloudy because it kind of naturally filters through the stream bed. So however you get the water to the well site, whether it's, again, piped or trucked, you still need to be able to store the water. Many times we're seeing earthen impoundments being installed, highly engineered impoundments to make sure that they're stable and they won't fail. So in Pennsylvania, they have to have a 3-to-1 side slope, and basically be less than 15 feet, or roughly less than 5 meters deep. And they need to stay out of the floodways, and in essence, not represent any sort of a hazard. Because what you don't want to have is, an impoundment like this fail, and suddenly you have, 20 or 80 million liters of water, running down the road. So they make sure that they're stable. They also need to be lined, so you can see the liner in that well pad. You can actually see they're actually actively fracturing a well at this adjacent well pad. So oftentimes these impoundments will be adjacent to the well pad, or they might have one well pad serving, one impoundment serving multiple well pads, that might be, say, a kilometer or two away. Again, reduces the overall surface footprint if you can have one impoundment serving multiple well pads. We're also seeing some more innovative above-ground storage being used out there. This would be what we would call a porta-dam. It pretty much is like a large above-ground swimming pool. To think about it like that, you could store maybe 2 to, say, 5 million liters of water here. The nice thing about these is that they can be constructed in a day or two and then be taken back down. So they're mobile, they're reusable, and you don't have all the earth moving associated with an earthen impoundment. So they have less of a land disturbance, which is, again, one of the sort of critical potential environmental impacts is disturbing too much land, altering the surface hydrology. If you can come in with these more temporary types of units, you, again, minimize those surface impacts. We're also seeing more vertical storage tanks be utilized out there in the field. I should note that this is only allowed for fresh water, whereas a vertical tank like this, you could use it for both fresh water or the produced water. So a little more versatile. Again, these can be brought into the site and taken off and used at another site once completed, again, minimizing that surface footprint. And the nice thing is because they're vertical, you can store more water over a smaller surface area. The flowback waters or the produced fluids, these can be stored in earthen impoundments, but they need to take a couple of extra measures of safety to make sure that the water resources aren't being impacted. And so whereas a freshwater impoundment only needs one liner, the flowback impoundments would need 2 liners that are thicker, along with leak detection systems and monitoring wells so as to ensure that there's no release from these impoundments. We're really not seeing too many of these being used out there. There were some constructed initially, but I think the industry sees that the more modular tanks are sort of a better option and maybe work a little bit better operationally, and also, I think have a smaller surface footprint, minimize the potential environmental impacts that way. But where these flowback impoundments are being installed, oftentimes they'll actually have bird netting over them, so you don't have waterfowl, ducks, geese landing in these. But then ultimately, once the wells are put into production, as the volume of fluids being produced from these wells drops off, you'll see these produced water tanks at the well pad, and then they'll again have secondary containment around them. And then these tanks would then be emptied on a periodic basis as they fill up, and then that fluid would be taken to a treatment plant or be taken perhaps to another well where it can be recycled for hydraulic fracturing purposes. We're also seeing many of the companies use what we call a closed loop drilling system. Initially, when many of the companies began operating in the shale basins, they would dig a small pit, put a liner in it, and then the drilling muds that they use to lift the cuttings out of the well and keep the drilling bit cool would basically be left in this pit. And so in there you have fluids that came from deep in the earth. You could have elevated total dissolved solids, the cuttings, potential for some of the naturally occurring radionuclides in there. And there were some tears in these liners, and there were some releases. And so over the last few years, we've seen more and more companies go to a closed loop system where the drilling muds are recirculated through a tank. The cuttings are separated off for disposal, primarily in landfills, and then the drilling muds are actually recirculated and recycled. So again, minimizing the potential for any environmental impacts out there. So want to cover the wastewater stream and what are some of the options out there to deal with these produced waters that, again, are going to have a relatively high total dissolved solids content and have things like naturally occurring radionuclides and metals like barium and strontium in it. Again, what we're seeing is a lot of reuse of these fluids. Pennsylvania has really been a leader in innovating the reuse of these produced fluids. Whereas in 2009, when the industry was pretty active but hadn't quite ballooned, you saw maybe 10 to 20% of these fluids being recycled. 3 years later, we're recycling on the order of 90% of these fluids. Different companies have different philosophies on what level of treatment of the produced fluids is appropriate for recycling. Some companies are simply blending the produced water with fresh water, sort of decreasing the concentrations of any constituents of concern in there and reusing it on the next well for hydraulic fracturing. Other companies are running the water through a treatment system. That treatment system might be actually on site. You could actually have a mobile treatment facility on site, or they might take it to a centralized treatment plant to have it treated. The nice thing about the mobile treatment facilities is that you don't have to truck the water to the treatment plant, because that treatment plant might be, 20 or 50 kilometers away. So the mobile treatment technologies would be considered to be a better management practice. There is going to be a portion of that wastewater that's not going to be recycled for whatever reason. That's sort of a decision made by the company. And so the balance of that water primarily goes to underground injection control wells, deep disposal wells. Again, in Pennsylvania, we don't have many deep disposal wells in our state. There's only 5 that currently operate. Some of the adjacent states, Ohio, just to our west, has about 179 injection wells. So much of our waste that we're not recycling is going to our neighboring states' injection wells. But if you go to, say, Texas, they have on the order of 10,000 deep disposal wells. And so recycling isn't quite as prevalent there because they have sort of the option to dispose of it, which might be more cost effective and maybe even more environmentally protective, rather than trying to deal with this waste at the surface, as long as your deep disposal reservoir is sufficiently hydraulically isolated. And this is just a picture of one of the treatment facilities that they bring the water into. And then this is a picture of what the flowback water might look like. It could have sort of a darker color. Sometimes bacteria will get in there and give it that dark color, have more of an amberish color. But once it's treated, it's actually clarified. And depending on the treatment, that might just involve removing the metals out of the water. So this water actually would be quite salty, probably 2 or 3 times saltier than the ocean, but can be recycled and reused for hydraulic fracturing. Yeah, we saw this plot last time. Again, in general, the more salty or the higher the TDS level gets, the less likely the companies are to be able to recycle it, because at some point it's going to cost more to treat it than it will be to just get a fresh water. So it's actually going to be maybe more cost effective to actually dispose of it. Again, we saw this. This would be some of the contaminants of concern in these flowback waters. So these would be some of the contaminants you'd want to have analyzed and know what those concentrations are. This shows a typical treatment scheme, and I'd mentioned the fact that chemical precipitation is the common treatment technology for these fluids. And so in essence, for one of these treatment plants, what they're going to do is bring in the fluid, run it through a sedimentation tank, which allows the sediments, sort of the particles in the water, to settle out. Then they would run it through a mixing tank and a flocculation tank. And this is where they add a coagulant that basically allows the metals in that water to drop out. And those are the metals that they're concerned about having scaling potential if this water were to be reused without treatment. So they're trying to get those scaling agents out of the water. And then it would be run through a clarifier. Ultimately, you would have a sludge that would contain many of the metals, as well as the radionuclides tend to drop out along with that and be in that sludge. And then the balance of the water can go back out for reuse purposes, or potentially disposal if it were to be disposed of. Facilities that are handling this sludge must have depending on what state you're in, but in Pennsylvania they have to have a radiation monitoring program to make sure there aren't elevated levels of radium or perhaps uranium that could be in that water. It's really not been an issue to date. Again, as I mentioned, the sludge waste stream is going to landfills. The landfills must also monitor the incoming radioactivity of the sludge, and again, it's really not been an issue. So the regulator set standards for each landfill, and as long as the radiation detectors don't detect above that threshold, the sludge goes into that landfill. The salt in the water, represents a challenge to remove that salt because it's an energy-intensive process to desalinate water. So that's why many of the operators will choose to remove the scaling agents, those metals, but leave the salts in. And again, if you recall, I'd mentioned the fact that we have brine-tolerant friction reducers. That's really sort of the key to allow the recycling of this water without desalination. There are some desalination technologies. You've probably heard of reverse osmosis. But reverse osmosis is fairly limited. If the average concentration of the total dissolved solids is maybe 70,000 in some basins, it's not really going to work. In some basins where the total dissolved solids is less than, say, 45,000, reverse osmosis might be a viable technology. There are evaporators. That's actually what this unit is. It actually, in essence, boils the water, and then that steam stream is recondensed, and that water can be recycled, and then you end up with a briny concentrate, and typically that's going to go to the injection wells and not get recycled. And then some of the other technologies that really aren't being used on any commercial scale that I'm aware of would be membrane distillation and ultimately crystallizer to basically turn that salt into sodium chloride crystals that could potentially have beneficial uses on for industrial processes or other commercial endeavors. And there are some companies looking at how to use these salts beneficially rather than somehow disposing of that salt. Again, I'd mentioned the fact that mobile treatment technologies are being deployed out in the field. These tend to be a more environmentally friendly approach because you take the trucking out of the equation, you're minimizing fresh water use, and so overall it's a better environmental approach, and it actually can be quite cost effective, largely because you're taking out the trucking costs. Different companies have different thoughts on how the flowback water should be treated and what would be acceptable for reuse. This is just sort of an informal survey I've had with some of the treatment plant operators and what their clients are requesting the water be treated to. And so basically, they're looking at getting the cations or the metals out of the water to acceptable levels, mostly barium and strontium and iron and calcium. That's where the focus on the treatment has been. Some companies are now finding that they're more comfortable having some barium and strontium in there, that the scaling potential isn't really as high, but they actually still have concerns for iron as a scalant down there. They want to make sure that the sulfate levels are sufficiently low because it's the sulfate that typically combines with the barium to form barite, which is a pretty significant scaling issue because it's very insoluble once it forms. And so once it's there, it's very difficult to remove. The total suspended solids, that's the TSS. That's just sort of the floaty particles in there. They want to have those out of there because they themselves can actually be a physical scalant. But again, the total dissolved solids can be variable, greater than 50,000 parts per million or milligrams per liter is pretty acceptable out there. There are some potential water resource impact pathways out there. And so these are really, again, to sort of emphasize, this is where we really need to be protective because water is something that everybody relates to. It's something everybody uses every day. And so it's really been high on the radar as far as the potential for environmental impacts. It's the potential for impacting water quality. And so, we have had some faulty well construction issues where there have been some mostly methane that's leaked up into the aquifers. But, the regulations have evolved to minimize that potential. But really, we can have the best regulations in the world. We need to have good people out there enforcing them, and we need to have good cooperation between the companies and the regulators. And I think in general we're seeing that. Surface spills can be an issue, whether it's a well blowout. We've had in the Marcellus several well-publicized well blowouts where fracturing fluids are being released uncontrollably for several hours to maybe upwards of a day until they can get that under control. And so that's never a good situation. But that's sort of the extreme as to what can go wrong with these shale wells. Generally, though, the impact from those incidents have been pretty localized. They're isolated incidents. We've had really 3 blowouts out of roughly 3,000 wells that have been drilled and fractured. So that's a relatively low percentage of failure. But really, 0 failure would be ideal here. We've seen tears in the liners in the fluid impoundments. Again, we're seeing the industry use more above ground storage tanks to minimize that potential for release. But even when you have tanks, you can have leaking valves. So we need to make sure they're getting inspected. We've had spills of diesel fuel and just fracturing fluids. Somebody drops a container of the fluids and it spills. That's why you need well pad liners and secondary containment. So these are pretty simple engineering options to make sure that these potential impacts are minimized. Really the most critical part of the operation is to make sure that the wells are being drilled. And we've seen really a complete revamp of our oil and gas regulations in Pennsylvania that you'll hear more about this afternoon. But really where the rubber meets the road here is to make sure that the wells are constructed properly in the upper 1 to maybe 3,000 feet, or roughly 300 to 1,000 meters, to make sure that the deeper part of the shale is hydraulically isolated from the near surface water resources, both groundwater and surface water, so that there is no potential for vertical communication there. As I said, methane migration has been an issue. We talked about some of these numbers in the last presentation, but methane does exist naturally in groundwater. You have to determine whether it's been there for many thousands or millions of years, or whether it's your new neighbor who just showed up because a well wasn't drilled properly. Again, it's relatively rare instance for a well to have a methane migration issue. There's probably been roughly a dozen cases that I'm aware of in the Marcellus, and that's out of 6,000 wells roughly that have been drilled. So again, it's relatively isolated. Where it does occur, it can in general be remediated through some additional cementing operations. And in a worst case scenario, if it can't be controlled by those means, then the well would need to be abandoned and filled in with cement. We have in Pennsylvania a recommended parameter list for doing pre-drilling water quality surveys. Really, again, I kind of touched on some of the most important parameters would be methane and ethane, the total dissolved solids, chlorides, barium, and strontium would be, if you had to have a top 6 or 8 list, I think those would be the ones that really tell you whether there's any sort of a pollution potential from gas drilling. So I guess I lied. I will say it again. Pre-drilling water quality testing is really critical with all of this. I'll probably say it later on this morning too. But again, understanding the geology is critical. Making sure the gas wells are constructed is critical. But I think, from an engineering standpoint and from the technology that's out there, there's potential for risk of contaminating the aquifer, mostly from methane migration, but it's pretty low. It's really the handling of the fluids at the surface is where more of the risk lies. It is an industrial activity, and it is energy development, so there are going to be some inherent risks there. So again, they obviously need to be minimized so that the benefits of these resources can be maximized. So With that, that will conclude part 2 of 3. So thank you very much.